Okay, I guess it's time to start. So today, before we get into class, I wanted to give some summary about lab logistics. First of all, I would like to encourage you to go on the website, both on B Courses and on Piazza, and take a look at what happens on the 7th lab, right, and how is it going to be organized and the like. So, hello, tick, tick, tick. Okay, so no more labs this week. Okay, so there are not going to be any additional lab work. So you can use the space, though, for the labs to start working on the project because you have all the equipment and stuff like that you can leverage for discussing your project. The GSI will be in the lab during the lab hours so that you can think of that as an extended office hours for the lab itself. So answering questions and meeting with each project group. And there is going to be about 10 minutes per week briefing for each group so that we can keep an eye on how well you're doing and what you're coming up with. The lab write-up 7, which is section 6.1.3 of your manual, the hand-in is next Tuesday, October 21st, but some of you have a Monday lab, and so it's just days. We thought it was too close for comfort, so we allow you 3 more days for the people who have the Monday lab. Okay? Yes? Excuse me?
Can you the lab on Tuesday during class?
I think you could, right? I don't see any reason. Shift by 3 days, so you have 3 additional days. So, I mean, if you want to bring it here, so since they are going to be here anyhow, you can do that, but it's not. Okay. So, so project guidelines. So it's time for you to really start thinking on the project because time is running and and projects are difficult to do, as we all know. So remember that the team is 3 to 4 people per team. So so just start looking around and see who you would like to work with. You can team with anyone in the class of your choice. I mean, you have to be, at ease with your group. You can post ideas and find groups in Plaza, so you can advertise, I have this wonderful idea, who wants to work with me on this project? That's allowed. Can be anything embedded, so it can be research-oriented or application-oriented, as you like, as long as it satisfies the general guidelines that were given before. So pay attention to realistic timelines, so don't find yourself at the last minute trying to whip up something. That's never a good idea. Do use models to design, so we just don't take as a good project one that is being done by screwdriving and hacking. So we would really like to see a thought process and a modeling part and a simulation part of your design. And we would like also to, again, to encourage you to have a good quality software architecture, which means decompose your program well, plan a testing strategy, and comment your code well. Okay, so this could be also considered as an exercise in good programming practice as long as we are looking at embedded systems. So remember that embedded systems require a different way of thinking because of the importance given to the physical properties that are associated with the software. So the way in which you come up with a good software architecture for embedded system is not necessarily the same good architecture for general programming. So you have to think along different lines. Okay. And choose your hardware very wisely. So just pick up among the list of parts that we gave you, pick up the ones that are really going to be good for your project and good for you, that you can work with. So timeline and deliverables. So October 21st, you have to have a project charter, which means groups and a outline of what your project is going to be. November 4th is going to be a project review with the GSI and mentors, if indeed you find a mentor in the department or wherever else. You will have to qualify with us if this is okay or not, but if it is an okay vote on the mentor and the project, then you can meet with the mentors. November 17, project mini updates. So we would like to see where you are at and what is going on in your project. November 25 is the project milestones, so you should have already a good progress on the project itself. And December 17 is project presentation. Now, we will start here because we have 3 hours of use of the class for exams. It's not going to be enough because you are 1,500,000, right, people here. So 3 hours is not going to be enough. So we also reserved other rooms to continue on. So the idea is to have you present for about 15 to 20 minutes your project. And we would like to see everybody involved so that you can see what your fellow students have done, and you can comment on it or have a feeling of how the class is going. And so that is going to be on December 17th. Right? So there was a question on Piazza, say, are we requested to be present at all presentation? Of course, you are not requested, but we would like to see you. So for at least the 3 hours of the class, of the exam, we would like to see all of you here. Then after that, you may have other exams, you may have to study something, whatever. So I understand if some of you misses it, but we would really like to see the maximum amount of people being present at the presentation. Now, I remind you that in addition to the grade, there is going to be, for the best project, I stick to my promise, it's going to be a nice bottle of Italian wine for the winner. But more importantly, it's for some of the best projects, since you are many, so it's likely that something good is going to come out. And so that something good, in general, I'm used to this since 40 years ago, but for the best project, we aim at publishing a paper in conferences or in journals according to what you come up with. So think along these lines. So maybe for some of you, the first chance of having something published. Okay, so think along these lines as well. So find a good project that can expose some of the material that you learn here, but can have that spark of originality that can be the subject of the publication in good conferences and journals. Okay, so December 19th is a final report, plus video, plus peer evaluation. So that's the very last moment in which everything comes together. Okay, so let's move on the topic of the class, and today we are going to talk about reachability analysis. Yes? Yeah? No. We said that we give you guidelines, right? So the guidelines were the list of hardware and stuff that we allow you. So don't go away out of the set of hardware that we gave you. So instead of thinking about exact project, we said, okay, take this platform as being the starting point for your project. Originally, we thought to give only 3 projects, and everybody had to pick one of these projects. But that was at the very beginning. But then we moved towards the idea of using platforms that are the same for everybody, right? So the list of parts is the same for everybody. So also because by doing this, we allow you to be creative on the application, and at the same time we keep it limited in the sense that you don't go everywhere and anywhere you want. And plus, you get also the design methodology that we presented, which is this is a component, so build up something good out of the components, and show me that you have verified your approach. But you are right. At the beginning, I was more directive. Okay. All right. So reachability analysis. So last time we were talking about temporal logic and how temporal logic is a good way of imposing properties to your design. Now, that's fine. You can formulate properties with temporal logic, and we say that the formulation is already a big problem. But once you formulate, what do you do with it, right? So remember that one of the good things that we wanted to say is that if you have formulated your property in a good way and in a formal way, then you should be able to verify that your design satisfies this property that have been captured in a formal way. So today is about that. So how you could do that, okay, and some very important results that were obtained in the last 20 years about how you go about verifying these properties. So I remind you that a typical problem that you may have in robotics or in other applications of embedded system is the fact that you want to reach a particular end state and you don't want to end up being stuck in any place. So you want to stay away from a bad set of states, and you want to be capable of reaching a particular state that is your goal state. Additional problem we said before is that instead of reaching only a final state, you may want to have an intermediate set of states that you want to go through. Now, all of these formulations can be done in formal terms, as we said before, in using temporal logic. Now, this one is another interesting application. What you see here is a graph of finite state machine modeling of two trains and a bridge traffic controller. So this is actually a German railroad, and the point is was actually done, right? So this was a formally verified design of the scheduling of the trains and of the bridge controller. And so the goal here was to avoid a collision path. Guess what? Yeah, that would be nice, right? And we know that sometimes the trains do go onto a collision path. And so a few years ago, there was a miserable accident happening in New York State when two trains collided because of the wrong scheduling of exchanges and green semaphores and red semaphores and the like. So it is possible if you don't plan it carefully. Okay, so this one was a result by this guy, Moritz Hammer, University of Munich. So people do use this technique to avoid accidents and the like. Now, reachability analysis. What does it mean, reachability analysis? Well, semantically is obvious, is that I would like to see where I can go. You know, how far can I go on my finite state machine? So I start with a state and say, which states can I touch? So this is a set of reachable states, whatever state that I can bump into. Now, if I could do this analysis, then of course I will be able to solve the problem that I showed you before, because if I have all the reachable state, if any of the reachable state is a bad state, that's bad news, right? So it means that my system has an hazard. I may end up in a bad state, so the two trains may collide. Not good. By the same token, if the reachable state contains the end state, it says, okay, I can reach my goal. So, hallelujah. So, by doing reachability analysis, I can solve both the problem of stay away from the bad state and ensuring that I get where I want to get. Okay. So, model checking is actually an algorithm that is capable of verifying formal properties along the set of reachable states. Now, mind you, model checking is probably one of the most used techniques in verification that I know of, short of simulation, of course. And the interesting point is that model checking has earned the people who propose this technique the Turing Award. And Turing Award is like the Nobel Prize of Computer Science. So this is indeed an important thing. Now, remember that temporal logic was, again, earned a Turing Award for Amir Pinwali. And this technique, model checking, earned the same award for three people. Was Emerson, Clark, and Sifakis. Okay, so these three people were credited with the idea of developing this technique. Okay, so what is a formal verification then? Well, the first thing is that you have to start from the model of your system. Now, remember that we would like to see whether, under all possible conditions in which my system work, that some good or bad good stuff happens or bad stuff does not happen. Okay. Now, the point is that when you think about all the possible conditions, what does it mean, all the possible conditions? Does it mean for all the possible inputs that we can dream of? Not really. What we have is that whatever the environment of this system can provide as input to the system under analysis, which means that I have to have a model of what the environment does. Okay? And when I do the formal verification, I'm going to combine two models, the model of the environment and the model of the system, so that I form what is called a closed system. So it's all inside one blob, right? So the environment and the system. And I want to show that this combined system has got certain properties. So the system and environment come in, you compose these two models. Now, if you have finite state machine for both, hallelujah. We know how to compose finite state machines. So, and we will see some example of how you do that. We already had classes on how you compose finite state machines, so that is reasonably well known. Then you get a closed system that we call M, and then you have the property expressed as temporal logic, and then you have an engine, which is called verify, that is going to see whether phi applies to M. If phi applies to M, hallelujah, you say, I have a working system. If it doesn't work, then the good thing about model checking is that it will give you a counter example. So it will tell you where it fails. Why is that important or interesting? Because it's a debugging mechanism, right? So if I know where it failed, I say, oh, I see what happened. And so to prevent that from happening, I need to do A, B, C, D, right? And so, in fact, this can be used to do synthesis so that you never get into a bad state, all right? And that will be the last slide of the class, how you do that, how you do the control. All right, so closed system, again, is that you take the environment and the system, combine them two together, and then there is no input anymore to talk about, right, because the input is contained in the world model. So you model the entire world in which you are interested in. So again, you obtain a closed system by composing the system and the model of the environment, and now you are all set to go to do reachability analysis and the rest. So suppose that you want to model check GP, which means that property P has to be globally true on all states, right? Now, on all states means on all the states that is on a trace of the system, which means for all reachable states, right? So let's say, consider an LTL formula from GP, where P is a proposition, and P, remember, is a property on a single state. So GP means that that property on a single state has to be valid for all the states that I can reach. To verify GP on a system M, I need to enumerate all the reachable states. And then for every reachable state, I have to say yes, no, it holds or it doesn't hold. If for one reachable state the property doesn't hold, then GP is false. Okay? If it holds for all the states that I can reach, hallelujah, it's okay. Now notice, yes.
You say that P is a property on a single state.
Right.
Property is something eventually happens.
No, that is a temporal logic. It's not a property. So the original property is, when we talk about P and we say GP, that is call it a global property, right? But P, when we say we use in temporal logic, the proposition is on a single state.
P is what you call the
Position. Exactly. No. It's a propositional logic. So it doesn't have the time involved. It doesn't have time involved. In fact, the G is a proposition, right? It's atomic proposition, right? On the single state, right? Okay. And GP is a property that is, okay, on a trajectory, so it involves time, right? So you have to express, and G is a temporal nature, right, of it. Okay. To verify G, and check that P is true, the state space explorer is typically represented with a graph. So what happens is that I start from this state 0, then I have 22 states around me. So if I go here, that is one step, and so the graph is the beginning of my trajectory, the next state of my trajectory, then I take another step, and by doing that, I build a graph, right? And so that graph is called the reachability graph or state graph of the system, okay? Now, when M is a finite state machine, this reachability analysis terminates, always terminates, in theory. Why do we say in theory? It does terminate, and it's okay in finite time. The problem is that you may have what is called the state explosion. So you may have so many reachable states, right, and so many things that you need to look at that in practice is almost if you had an infinite set of things to do. So you will never be able to do it. So this one is also called the curse of dimensionality, and it is one of the major impediments of using this technique for any problem. So remember when I said brute force never works? So if you apply brute force, which means you are going to look at all the possible states that you reach, and you are going to visit all of them without thinking about it, and your state is representing the tiny little details of your implementation, you are out of luck. You will never be able to verify that system, so you have to stratify and use layer of abstraction. And at every layer of abstraction, you have to have a reasonably simple problem to look at, because then the techniques will apply, and you will not be out of luck. And so if you have a certain relations between the properties, a different layer of abstraction, then while you are moving down towards implementation, you still keep the state space small enough, you are guaranteed that in the end, when you compose back everything, the original properties are satisfied. Okay? So that is a very important point to say, meaning then when you get to formal verification and the like, you always have to have a guiding principle, which is design methodology. So freedom from choice. Limit your choices, because otherwise it's going to be too difficult to do anything. In fact, the number of states may be prohibitively large, and so you may not be able to perform the complete analysis. Now, let's get back to our nice example of the traffic light controller. And the property that you would like to say is globally true that green and crossing is not true. Why green and crossing is bad news? Because it's green for the cars and the pedestrian walk, right? Not a good idea. Bad news for a pedestrian. Maybe for the car driver, say, yes, finally get the turkey. Wow! You know, if you go to Italy, you have got to watch out, because that property is not necessarily verified. Okay, so. But we are in the United States, and in general, if you're a turkey pedestrian that crosses the road in the middle of nowhere with a freeway, you know, cars stop, right? So this is amazing feature of Berkeley in particular, right? And anyways, right? And so in fact, I got flagged by the police. There was a guy, right, which was about this far from the border of the crossing, right? And he was walking towards it, and I was coming, I just crossed, and I just went, right? The police said, oh, you didn't give precedence to the guy. I said, wait a minute. The guy got to the crossing when I was to the next crossing. So I didn't try to kill him, you know. I mean, why should I stop? If I stop everybody else, right? And so sometimes you have to optimize, right, a little bit, because otherwise you stand still, and it takes 35 minutes to do 3 miles, like myself this morning, right, to get to work. Why? Because sanitary project, right? That's not good. It's not optimized. It's not good embedded project. 0 to the city of Berkeley. They are failing, okay? F grade, okay? So don't do that in your project. So I'm going to check personally if something like this happens. All right. So coming back to the real story, even though that is a real story, and this one is an abstraction of the real story. So, okay, here you have on the left the model of the traffic light. And on the right, you got the model of the pedestrian. Okay. So now, which one is the environment and which one is the system under design is rather clear. The pedestrian, I would like to design a pedestrian. The ideal pedestrian never crosses, stays put. Right? So cars go. Right? Anyway, so, but we have a model, which is the model of a pedestrian, which is the environment, and we have what we are designing. And so the composition of the model of the pedestrian and, and of the traffic light controller should give you that notion of the fact that you never get into the bad state, which is a bad state is where not green and crossing occurs, right? Okay, now, we compose the finite state machines, and you get this finite state machine here. Notice that this simple Turkey problem has got by itself 189 damn states, right? So 189, when you think about, you compose a machine with 5 states on one side and 3 states on the other one. When you multiply and all of that, boom, 189. Why? Because if you do not an extended machine, but a finite state machine, then for every count you have a new state, right? So new state, new state. So you got to consider that. So in any case, this is a compact representation of the combination of the two finite state machine. You have a variable which is count 0 to 60. And then you have the following state space in which you can start anywhere you want, so initial state. So suppose that you start from red crossing. And so until the count reaches 60, you stay there, so you have a self loop, and the pedestrian can cross, and then when the count reaches 60, you set to 0 the counter, so you reset the counter, and you go to green and none, meaning no pedestrian is going to cross. Okay. Now then, you got to count again in green, and then you go to pending and waiting, meaning that some pedestrian shows up. Then the counter goes up, and then you go to the next state, which is yellow, waiting. Now, if pedestrian doesn't show up, you can go directly to green to yellow because you want to have some regularity in which the traffic light goes from green to yellow to red. Okay, so this is the composition of the two machines. Now, a reachability analysis, we would like to see again if I can get into a situation where I can see the pedestrian crossing and the light is green. So now, you always say, well, gee, we have a finite state machine, the one I show, I just go tum, 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 and I see what happens, right? So unfortunately, 189 states to do tum, 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 you don't have enough space on the whiteboard, blackboard, computer screen, too many, okay? So what happens is you have to think as a computer thinks. So a computer doesn't have eyes, so the actual representation, graphical representation of the state doesn't make a damn difference, so it doesn't care. Now, if you think carefully, what is the best way of representing a finite state machine? Do you want to give all the state one by one and the arc that go from one to the other and all that? Not really. What you would like to do is to give the rules according to which you generate the next state, right? And so remember that we have two functions, right? So actually a relation. One is a next state relation for non-deterministic finite state machine, or a function in the case of deterministic finite state machine. Given where you are, I can tell you where you can go, right? That's a next state function. And there is the output function that says, given the state in which you are, given the input which you are, that's what you're going to see at the output. Okay, so these are the implicit rules that give you the famous graph. But it's implicit, right? I give you through functions. Now then, when I do reachability analysis, what I'm doing is essentially applying these rules, right? Applying next state, and I get the next state, which could be single state for a particular input, a set of states non-deterministic, or if I want to see for all possible inputs, I'm going to see only the next state function, in which I'm going to, quote-unquote, consider all possible inputs that can present to this state, right? That's the way in which I construct the state graph on the fly. So I start from the initial state, and then tum, tum, ka-chung, 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 I generate the various states. So we start with initial state and explore the next state using a suitable graph traversal strategy. So suppose that I'm at state 0, okay, so at the beginning. So now I have a bunch of next states, right, next to me. remember that I want to explore the reachability, right? So how can I explore this finite state machine? For sure, I have to take a step, right? Boom, right? Now, I can do two things, right? So I can go back to state 0 and generate the next. And I come back to state 0, generate the next. So what I'm doing is that I'm exploring all the states which are distance 1, which is called breadth first search. So you do like this. You're like a fan, right? You're opening a fan. So everywhere I can go from this state, I generate. What is another, and you don't answer, what is the other strategy? So that is called depth first. So your friend here said, go to the end. So what happens is that I'm here, I go here, then I don't go back and I say, where can I go from here to the next? And I pick 1. And then I say, where can I go from here on? And I pick 1. When can I go from here on? And I pick 1. Okay, so that's called depth first. Now, when I see something that I've already seen, then what do? I back up, right, to the previous state, and I do another step, right? So that's the way in which I traverse. Depth first is an incremental strategy which tends to go all the way to the end as many times as I can, right? The other one is that I go everything, 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 everything. Now, which one is best? Either one, right? It depends on the particular graph that you got, right? And so, in fact, there are deep graphs in which depth first, of course, and shallow graph where breadth first is much better. Okay, so you cannot say a priori. So either one will work. But in the case of implicit techniques, most of the times it's better to go breadth first for the following reason. We'll see how it goes. So the depth first search, we said before, you maintain two data structures. One is the set of visited state R, so it's a set of the states that I've seen. And then a stack with the current path from the initial state. So I went through state 1, state 5, state 7, state 22, right? And I'm in state 22. Now, if I generate state X, which is the next state, I may be in state 5. Guess what? I already visited it, right? So I have to stay in state 23, try another path. That is the way in which the stack is working. Now, why do you want to keep the stack? Because you want to know where you have to back up, right, to start another search. And then when the entire stack has been visited, you have visited everything. Okay? Now, that's the reason why you need the stack. Not only. Suppose that when I do this depth first, I get into the bad state. Remember that I wanted to have a counterexample? What is the counterexample? The content of a stack, right? That is a path that violates the property. So here we go. So that's the reason why you need this dual, data structure that you are going to use, the set of state R and so if the depth first algorithm finds the target state, okay, how can you generate a trace for the initial state to that state? You read the stack and that's it. We already said it. Very, very simple. Simply read the trace. Now, this is also called explicit state model checking example. So why explicit? Because we have the entire graph in front of us, so we are not generating it on the fly. Okay. So because we want to show what happens. So first of all, you have to pick up an initial state. So in this particular case, the initial state is red crossing 0. Count 0. Your red traffic light and pedestrians are crossing. So that's the initial state. Now the next one is red crossing, and you bump by 1 the counter, right? And then the way in which this finite state machine works is that you keep on going until you reach 60, right? And which are all the self loops. So that's the first. And that is, no matter if it is breadth first, depth first, there is only one path. So it doesn't make any damn difference. Now, once you get there, if you want to do depth first, then you say, for example, I go to green none, okay? Green none 0, green 9 1, and so on, right? Green none 60. And then what do? Ha! Now you have two paths, right? Two potentials. You can go yellow waiting or pending waiting, right? So if I do that first, I choose one of the two. In this particular case, say that we do, if I remember correctly the slide, we go to yellow weighting. Yes, I got it. Yellow weighting 5, and then you move on. But if you move on, you get to red crossing, and you already seen that state. So what you have to do, you have to backtrace to the previous point, which is green none, and you generate the next state of green 1 that you have not visited before. And the next state that you have not visited before is pending waiting, and so you stay there 1 up to 60. Now, once you are through waiting 60, what happens? You go to yellow waiting, right? But yellow waiting you already seen, so this is it. That's the complete reachability analysis. That's all the traces that you find, the graph of the state, right, space, and that's it. So you have concluded the analysis of the state. Now, the symbolic approach is a different one, and so this one actually came later, and there was the key guy into this was Ken McMillan, that has been a lecturer in this department, and he was at the Cadence Berkeley lab. And he had an idea, and he said, okay, now, can I use a particularly efficient data structure to represent Boolean functions to make this search faster? And in fact, once he had applied this methodology in his thesis that won the ACM Best Thesis Award, now he said, well, if I can do that, then the number of states that I can deal with is going to be very large. And the answer is yes, if the finite state machine is large, right? Some sense, it's broad, right? This is certainly true. And in fact, he showed, it was a paper kind of tongue-in-cheek, but he said that he could explore in very quickly 10 to the 30 states, right? 10 to the 30 is a humongous number, right? Is more than the molecules that are present on the Earth, right? It's humongous number. But he demonstrated you can do that. Easy, broad graph, you can do it. So anyway, but the point is that instead of doing the explicit search, I'm going to represent all the next state, right, in a compact way. So this is the idea. So it's just representing things in a compact way. So now, in order to do that, he had to convert the problem of visiting states in a logic problem or in a Boolean function, because remember that this particularly efficient Boolean structure applies to Boolean functions. So I need to convert the reachability analysis into a Boolean function representation. Okay? So set operation can be performed using Boolean algebra. We know that. Represent a finite state S by its characteristic function, which is a Boolean function. What is a characteristic function? Is a logic function that evaluates to 1 if X belongs to the state S. So a set of state S. So we have a set of state which is called S, and we want to see whether state X belongs to this set. That is a characteristic function of X, right? So so f of S X is equal to 1 if and only if. But if and only if in the sense of definition. It's not a theorem. So it's a definition. So if X belongs to S, this function is equal to 1. Now, this is a Boolean function, all right, okay? So I can represent this Boolean function with this fantastic representation. But now, the interesting point is that this characteristic function, if we want to say, does X belong to the state S? So the answer for reachability analysis will be, does this state belong to the reachable set, right? And so how do I then convert that into this question? Well, remember that the next state function or relation is exactly what gives me what I can reach in one step, right? So what I will do is that I will keep on doing like this and ask the question over and over again. Does X belong to that set of new reached set? So what I need to do is that I need to increment at every step the set of reached state. And I keep on asking, does X belong to that? So, but if you think carefully, I can represent the next state function as a Boolean function. In what sense? How does that work? Because if I'm in this state, I'm going to encode this state. right, with a Boolean representation. So suppose that we have, let's make 4 states, right? How many bits do you need to represent 4 states? 2, as your friend here, who's a rich man, who knows Boolean function really well. 2, right? Because I have 0, 0, 0, 1, 1, 0, 1, 1, okay? Now, if I want to say that I go from state 0, 0, can reach 0, 1, and 1, 0, how can I express that? Is I just express as a relation, right, between the bits of the states. So the next state function is going to be the Boolean function that has as domain 0, 0 and as range 0, 1, 1, 0. And I can build that with cubes or with whatever, right? So I won't tell you how this efficient data structure works. It's called BDD, binary decision diagrams. You can represent any Boolean function with a binary decision diagram. Now, you know, I bet all of you know about the Quine-McCluskey minimization procedure and the way in which you build a function, a logic function with cubes, right? Cubes are essentially, you know, vertices of, in this particular case, of the square, but of any Boolean hypercube, right? So you can cover any logic function with points in this cube space. And then you have a sum of product representation of the logic function. But there is another way, which is called BDD. And if you want to know more about BDDs, I'll just tell you what it is. You can go and take 144, and 144 will tell you about what a BDD is. At this point, for this class, it will suffice to say that there exist programs that do that based on this very efficient representation of Boolean function. Okay. And the Boolean function of interest are the next state function. That's the only thing I care. You know, that's what I'm going to represent. So the symbolic approach, or breadth-first search, is you generate a state graph by repeated application of a transition function. So I get at once all my next state, and then of all this next state, I'm going to get all the next state, and so on. So it's called breadth-first because all of a sudden you find, you know, this very wide thing, right? That it keeps on growing. If the goal state is reached, stop and report success, else continue until all states are seen. So you go from Q0 to Q1 by repeated application of delta. Then you go to Q2, then QK, and if you get S, hallelujah. And then there is a way in which you can trace back the set of states that you need to visit to get to S. For example, if you want to generate a counterexample. There is a way. I'm not telling you how to do it, but there is a way. Okay. So the symbolic reachability algorithm then is very simple. So you start from a set S0, and so the reachable set of S0 is S0, right? It's the beginning. Then I build an algorithm. I do the symbolic search. So I call R new equal to R, so it's the initialization of the algorithm. While R new is different than the empty set, what I do, I say R new is the set which consists of the state that I get from one step, but purified by the things that I've already seen, right? And so, of course, this is a set of new states. So I eliminate the states that I've already seen, and whatever is left is the set R new. Why then I focus on R new? Because when R new is empty, means that I visited all the states, right? So that's what it says. So R is R union R new, and so you loop around. While R new different from 0, I repeat that operation over and over again, and then I end. So this one is a symbolic. It's called symbolic again because the representation of the next state function and of the set is based on this implicit representation, which is called a Boolean decision diagram, binary decision diagram. Okay, so binary decision diagrams, and Boolean satisfiability is another technique to figure out if the state belongs to a set of states. So it's another way of doing reachability analysis, and that is yet another way in which you can do that. Boolean satisfiability actually works very well with depth-first search. Binary decision diagrams is the implementation of breadth-first search. Now, there are programs around, many programs around, that you can download from many universities and all the rest, that performs the implicit search of a finite state space. So there are programs that do, in the open domain, they do this analysis. Now, interestingly enough, there are also proprietary programs that work on trying to verify properties, temporal logic properties, on finite state machines. And the name of the game is to be able to cope with problems that are essentially difficult because of the number of states. Now, remember that I told you that sometimes the depth first works better, sometimes depth first works better. By the same token, sometimes satisfiability works very well, sometimes the BDD technique works very well. So what do these programs do? The one that costs $1 gazillion to buy, they use combined techniques, right? They try one, and then they see, doesn't look too good, and then they switch to the other one. Okay, so it's a continuous ping-ponging between different techniques, and so it's a heuristic. So the way in which you deal with the search is heuristic. The most important thing is that in the end, you got to reach all the reachable states, because otherwise you don't solve the problem. So sometimes people use heuristic to say, well, it works, it doesn't work. Now, in this case, the heuristic is in the way you go about doing the complete analysis. So it's a different thing. So you're not cutting corners on the final result. You are trying to invent new ways based on intuition or whatever that will give you the right answer in the fastest possible way. So this is not a dangerous heuristic. The dangerous heuristic will be, looks good, this is okay. Right? That's very dangerous heuristic. Right? Very dangerous. You can get, yes? It's still hard problem. So what I said is that there is enough, both of these two problems, in general, are NP complete, right? So there's no lack. It's exponential in the worst case. In the worst case. So not all problems exhibit the worst case. And so that's the reason why you ping-pong between the two. There may be particular problems where both of them don't work. Tough luck, because otherwise we would prove P equal to NP, which is impossible to prove, right? So that's impossible to prove. Nobody is even being able to start a proof along this line. So it's very unlikely that P equal NP. I don't think it will be ever possible to do that, but there is no proof to the contrary. So, one of these interesting logic problems, right? So, but the question is that this is a hard problem no matter what. Satisfiability is the father of all, or mother, according to what you like best, is of all the tree of NP complete problems. It's the root of the tree. So it's the mother of all bad situations. Right? That's it. Now, yet, if you look at some programs that are around, for example, I don't know how many of you have designed logic circuits, but if you use Synopsys Design Compiler, which originated from here, from Berkeley, with a program called MIS. Now, if you look at any of the subroutines that are in there, they always solve NP-complete problems, one way or another. Yet it goes, right? We can solve 100,000 gate optimization problem. We can solve a 1,000,000 gate now. 1,000,000 gate problem. Now, if you think in terms of Boolean functions, the size of this Boolean space is immense. Still, we can do it. Why? Because we got the right heuristic to visit the space, right? Okay, and so that was the secret sauce in the so mega lesson to you guys. So for your future. So if one says, oh gee, this problem is impossible to solve because it's NP complete, you say maybe, maybe not. This is not an impediment to try to solve the problem. Okay? So you can find ways in which, by using very good techniques, you can get to solve the problem in most of the cases, which in most of the cases is what you're looking for anyhow. Right? So don't give up. Now, not even when the problem is undecidable, which is, yet another horrible thing with respect to NP complete. Don't be scared. Go at it, right? Because if you do indeed find the solution, hallelujah. Now then, after 2 days go by, or a week go by, or a month go by, and you can't say a definite answer, when you declare defeat, and when you try to say, well, looks good, okay, right? So this is the last resort. It always looks good, okay. Don't trust that, but when it comes, it comes. All right? So, and this is very important because if you, in some sense, it's very good to use formal techniques. It's always extremely good to use formal techniques and to use mathematical properties, but sometimes are a good excuse not to work hard enough. Okay? Don't do that. So in application, you always have to find the way to go around the difficulty. One way, as we said before, is to restrict the space. Right? So an NP-complete okay, I was thinking it was raining. No, it's not just falling leaves. Now, the point is that if you have a limited space, even if it is exponential, if I have, say, 10 variables, 2 to the 10 is not that big of a number. I can do it, right? So even in the worst case, I'm still okay. So the point is that how can you be clever to reduce the size so that you can go about it? That's a heuristic, one possible way of solving the problem, reduce the state space. Okay? We'll see how you do it. Okay. Boom, boom, boom. Come on. Okay. So set of reachable state. This one is symbolic model checking, in which you say variable red and variable 2 is crossing and count is the other variable. So if you say the next state from the red crossing is described by this logic function, right? So which is the ending of different clauses. So that is the logic function gives me the next state. So count less than 1, count less than 60, and so on. So that is the logic function that generates the next state. Now then so I get all the states that I can reach when V1 is green and V2 is equal to none, and count is equal to 0, to count from 0 to 1. And then I can do V1 pending and V2 waiting and count equal to 1. And then I keep on repeating. Then I can replace V as V1 pending and V2 waiting and 0 and count between 0 and 60. So I'm building the set of reachable state in an implicit way. And then once I reach count to 60, then I go to the other one, which is V1 yellow, V2 waiting, count less and count equal to 0. Count less than 5 is all the states that I can reach from V1 yellow and V2 waiting. And that is the entire set of reachable state described with a Boolean function. Okay, that's the way in which you would do it, and that representation of Boolean function can be done efficiently. So I told you, we want to restrict the space. So, I mean, this is trivial, right? So we can do that, believe me. 189 states is nothing, right? But as a principle, what trick can we do to reduce the space? The trick that we can use to reduce the space is to say, what really matters for the problem at hand. So if I'm going to discuss, I don't know, about pedestrian, I don't care about cars, can we remove the variable cars from the description of the system, right? If it doesn't matter what the condition under which I go, the counter, doesn't matter, right? Can I eliminate that variable? Now, if I can do that, then all of a sudden the dimension of the problem drops down almost to nothing, right? Now, this one is called localization, right? And actually, Bob Kurshan, who invented this simplification technique, did this while he was in Berkeley. In fact, it was implemented in this, and we have gazillion papers talking about these localization techniques. So simpler models have smaller state spaces and are easier to check. The challenge is to know what can be thrown out. And so a simple useful approach is called localization abstraction, which means get rid of all the variables that are not present in the formula that you want to prove. So you hide the state variables that are irrelevant to the property that you want to prove. Now, is that sure technique? Does it always work? Unfortunately, no. Okay, so if you localize in this way, you may still have some of the hidden variables that make a difference. Especially because if you hide variables, then all of a sudden you get non-deterministic machines. And so if you take one path instead of another one, you can say everything is bad, because you have all these, non-deterministic choices. but may be still okay because that path you are not going to take. But remember, since I eliminated the variables that are going to differentiate between him and him, I don't know. So every time I hit a counterexample, I should refine the model and see if that is a real counterexample or not. If it says fine, hallelujah, I'm sure. Because what I did is that I created a larger reachable set by doing the simplification. Absolutely.
We already have a way of checking, of comprehensively testing all constraints and
No, in fact, and we do. No, we do. But I can answer the fact that my system doesn't have property phi. Why? Because the non-determinism that I generated is a fake non-determinism. It's really, the original machine was deterministic. It became non-deterministic because I threw away variables. So I may say that my property is not true because I reach him, because I don't see the path that takes me to him. And that path may be an invalid path because I abstracted, so he became reachable.
Okay, that's because you abstracted too much.
Exactly, and so now you have to back up. But when you do localization abstraction, you don't know if you abstract. It's a heuristic, right? You say, this is a way in which I'm going to abstract. And that is what I'm saying is that it sounds very reasonable. You say, hallelujah, that's a good idea. What I'm saying is that, yes, it is, but no, it may not be. So if the answer is going to be yes, the property is satisfied, then you're sure that it's okay, which is very good. If you get something bad, because I get to him, he's the bad guy, right? Then maybe that the indeed, but maybe that the sequence that gets me to him is an invalid sequence, so I'm never going to hit him, right? But I need to explore it. So every time I have a counterexample, I trace the path, and I explode. I come back to the original graph along this path. So it's like I take a very high-level view, and then all of a sudden, boom, and then I need to go with the Sherlock Holmes lens to see what happens in details. Okay, so that's it. So this one, you see, I threw away almost everything, right? This finite state machine has got true all over the place. So because there was no variable that was of interest to me on the input and output set. So what this says is simply saying what is reachable, but doesn't say how, right? And so if indeed I see the bad state red and crossing, right, it doesn't mean that red and crossing is really reachable, right? Because this is everything goes, right? All right, so a safety property, say that nothing bad ever happens, and as finite length counterexample. Now, a liveness property, remember that we have two sets of properties that we may want to assert on the system. One is safety, that means nothing bad happens, so I don't hit the bad guy. Instead, the liveness property is that I keep on getting the good guys, right? So, now, which one between the two you think is simpler? I already told you, but it's written down. But liveness is a bastard of a bastard of a bastard of a bastard of a problem. Now, safety is easier. It's still a bastard problem, but it's not a bastard of a bastard of a bastard of a bastard problem. Okay, so we have 3 levels of bastard less, right, in the safety problem. And in fact, if you look at papers, 90% of the papers talk about safety properties. And you wonder why? Because liveness is, again, a very complex problem. Okay. So now, suppose that we have a robot that must pick up multiple things in any order. So you want to pick up item I, where I is 1 from n. How would you state this in temporal logic? Any wild idea? So I want to make sure that I pick an object up. So. Yeah, he's right. So what I want to say is that F, eventually, I get to phi 1, so I pick up one object. And then he says and, so F for phi 2, because I want to go through phi 2 as well. But remember, in any order, right? So that's the reason why and, thank God, is commutative, right? So that's it. Okay, F phi 1, blah, blah, blah. you can actually also kind of nest this proposition. So how would you state this goal in temporal logic? We can also do this. The goal to be achieved is actually f of phi1 and f of phi1 and da 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 da. So you can nest it. It's the same thing, but it's more complex. So suppose we just want to say, eventually I get to phi1. So eventually I pick up object 1. Okay? So how would you go about doing that? Right? So because this eventually is kind of a funny property. Remember that it's very good to state everything in global, right? Global is good, right? Because it's safety. Global is good. F is not so good, right? So is there a way in which I can take this f of phi1 and convert it into a global? We already saw it when we did temporal logic. Does anyone remember it? Yes? Right, exactly. It's not G, not phi1. Exactly. So here it is. Phi1 is not G, not phi1. And so therefore I can construct a counterexample to G, not phi1, and the counterexample is a trace that gets the robot to the good place. Okay. So that's it. Very good. So I see that someone is reading the book or is following the class, or already knew the stuff, which is not fair. Okay, so this the last discussion. So by the way, if you want to, for example, suppose that you want to construct a controller that gets you to phi1. How would you? Okay, so we know that G of not phi1 is a counterexample, right? So it gets me there. So what would I do to build a controller? So something that makes my system go where I want. So that is a control strategy, isn't it? So it's which will get me there. So the trace. So what you do is that you create the input, right? The controller will create the input that will generate that path, right? So all of this, there is always two faces to the coin, right? The two faces of the coin is that one face is verification, and the other face is synthesis. If you're looking at formal techniques, they really are very much related to each other, right? And so, in fact, if you look at all the literature that talks about controller synthesis or formal verification of temporal properties, essentially they use the same techniques, essentially, right? Because as we saw here, there are two faces of the same coin, and the same coin is the reachability set and how you reduce or enlarge the reachability set if you have a bad state which can be reachable, or if you have a good state which cannot be reached. And so all of this give information how you should set up the controller, so the synthesis problem, to do what you desire to do. Remember, the control is a wonderful thing, right? Because you have a horrible system, right, that may explode in your face. You know what is the most horrible system from stability point of view that man has ever created and still works? Is the fighter jet plane. It is so unstable you would not believe. So with no controllers, the thing will crash in 1 nanosecond. Right? And why is so unstable? Because unstable means fast. Really fast. Maybe too fast, right? And so what happens is that you want the thing to change state, right, as quickly as possible. So if you have an unstable system, oh boy, you just boom, move there, right? But then you say, stop, before you crash, please, right? So controller. So the controller takes an horrible system that does whatever it wants to do, and it's going to make it do what you want. Now, then you look at all the literature of control, and then you see what a controller really does, and it's amazing and mind-boggling. What a controller really does is to erase the original system and to replace what you want to do as the real system. It's simply erasing, just canceling completely the original system. And then if you look at all the mathematical techniques are how you're going to kill the original system. So the famous controller for finite state machine is essentially saying, I don't care what the real system does because I'm going to eliminate it anyhow. So, and you are replacing it, right? So it's like, this thing that you take a bacteria and then you gut it out, you put the new DNA and you make it do things. So it's the same thing, right? You are gutting the real system out and you're replacing what you like to be. And it's amazing that it works, right? It does work. Otherwise, plane would not fly and car would not drive and all this nice stuff. But if you go to the bottom line, this will never be said in any class on control theory, but this is what it is. Right? So reread your control manuals and stuff and try to interpret in this way. Then everything will come crystal clear. All the techniques that are related, the notion of control, observability, all came down to this very simple principle. Right? Okay, so that's it for today. Questions? Apples, oranges? No. So I don't get to eat today. All right. Yes, there was a question? No, you did like this. Okay. It was an involuntary motion.